All right, for this next question, it's going to start off like our first question did here. I'm gonna ask you to calculate the frequency here first. C equals lambda times nu. We need to figure out nu, and that's c divided by lambda. Okay, c is my speed of light. It's given on the top of the page, and we also used it in the last couple of examples. And then this needs to be in meters, and this is 6.32 times 10 to the minus 7 meters. Okay, this ends up being 4.74 times 10 to the 14th per second. Okay, we're immediately now going to use this information. First, let's kind of cut up this sentence a little bit. So it asks, what is the energy of a mole of photons of this light? So we're going to have to figure out what's the energy of a photon and then how much energy is in a mole of photons. There's an equation for this, E equals h nu, where this h is a constant. It's called Planck's constant. It's up at the top of the page, but I'm going to rewrite it down here just so we have it. H is equal to 6.63 times 10 to the minus 34 joules times seconds. Okay, and what these photons are, it ends up that light behaves like a little stream of really tiny particles. And so rather than being this just long continuous wave, it actually behaves like a stream of particles. And each of those particles have just a little bit of energy that depends on the wavelength frequency of the light. So E equals h nu, and h is 6.63 times 10 to the minus 34 joules times seconds. And we just calculated just above there, 4.74 times 10 to the 14th per second. Okay, really conveniently here, second and per second cancel because we need this to just be an energy unit that's here. So E is equal to, put it in my calculator, 6.63 times 10 to the minus 34 times 4.74. Come on, big fingers. 4.74, there we go, times 10 to the 14th. Okay, and so the energy here is 3.14 times 10 to the minus 19th joules. Okay, and as far as the unit, this is joules per second, this is joules, but it ends up that we have a way of writing this that's better. So the energy here is equal to 3.14 times 10 to the minus 19th joules per one photon. Okay, this equation gives us the energy of just one of those little tiny packets of light. Well, okay, so we know the energy of a photon, and we need to know the energy of a mole of photons. I'm going to rewrite this here. 3.14 times 10 to the minus 19th joules per one photon. And it ends up, good old Avogadro's number works even for light. So anything that we're counting. So 6.022 times 10 to the 23rd photons equals 1 mole of photons. Okay, what's going to happen is this really teeny tiny number that's 10 to the minus 19 is going to get multiplied by this really huge number that's 10 to the positive 23. And now we're going to get a number that's pretty big. 3.14 times 10 to the minus 19 times 6.022 times 10 to the 23rd. Okay, I get 1.89 times 10 to the 5th joules per mole. Okay, and it doesn't take a long time to get a mole of photons. So the light's extremely fast, And so a mole of photons actually conveys quite a bit of energy. And so we can add a lot of energy into something like a chemical reaction by shining the appropriate wavelength of light on it. Okay, this is a ton of energy. This is actually much more efficient than heating it. So putting it over flame or over electric heating element, this is a much more efficient way to do many, many reactions.